Okay, good afternoon, everyone, and many thanks for Yeyong's host. It's my great honor to have the opportunity to present my ongoing here because it's ongoing work. So your comments will be very highly appreciated. The title of my talk is a cluster approach to scaling OpenFlow control plan. The work is deals with how to scale the SDN control plan using a computer cluster. Maybe everybody knows that self-defined network is now a very hot topic. The basic idea behind the SDN is to decouple the control plan and the data plan in the network. In a traditional IP network, the control plan and data plan are combined together in a specific device. For example, if we buy a switch or router from a specific vendor, the control plan and the data plan and the applications above the control plan are all combined in a single device, that is the router. But under the SDN framework, the control plan are separated from the data plan. That is, if a vendor provides a device, it can only include the data plan elements in the device, and the control plan is a separate component. In this framework, we can use the control plan network operating system from a different vendor, and the control plan software and the algorithm can be customized. With the decoupling, we can have the following advantages. First is the vendor agnostic feature. If we separate the control plan from data plan, the two plans can evolve independently. So we can buy the control plan software from a different vendor other than the same as the data plan devices. For example, we can buy a switch from Cisco, but we can use the control plan software from another vendor, for example, Juniper or even Big Switch or some other companies. So the two plans can evolve independently. Another advantage is that the separation brings control plan programmability. That is, you can customize your own algorithm, routing algorithm, with separate of the control plan and data plan. In a traditional network, the control plan and the data plan are combined in a single device. You don't know what's in it and how it runs, so it's a black box. But in the SDN framework, anyone can program in the data plan, so you have more flexibility in control your network. And the third advantage is that with the SDN, we can have a logically centralized network view. In a traditional network, each device is separated from another device. So the information, if we want to get a centralized view of the network, it will be a very hard work. But now with separating, we can have a logically centralized view of the network. That's every switch in the data plan will be a dummy device, so it can perform only the fast speed forwarding. But the control plan is more intelligent. It can make the more sophisticated decisions other than simple store and forward. The SDN framework is a good idea, but it also raises some scalability concerns. As I have mentioned, that the data plan in the SDN framework, the device only are only responsible for the high-speed forwarding. So the data plan device, usually a switch, only perform the high-speed forwarding. That's enough. It will do nothing else. So usually the device is implemented use ASICs to achieve this goal. The high-speed forwarding is the only goal of the data plan. But the control plan will be more complicated. Every flow that goes through the switch, the control plan will be responsible for every flow that goes through the switch, makes a decision where to flow where to forward the flow. So if the number of flows increases, or the number of switches increases, or the number of state packets increases, the controller will face a bottleneck because the resources on the controller is limited. So if the number of flows increases, the controller have to make more decisions on how to forward the flows for each flows, and therefore the computing capability and the other resources will be a bottleneck for the controller.
A quick question.
Yeah.
What size data plane are you expecting to create saturation in a control plane of that?
You mean the...
Because the whole entire point behind the flow abstraction is to sort of quell the amount of traffic that's being pushed up to the data plane in the first place.
Yeah.
So like the numbers I saw from Big Switch guys was that basically the size of the data plane has to get really, really big before you have to worry about scalability issues on the control.
Yeah.
So like how big of a data plane are we talking about?
You mean how many switches the data plane will control?
Well, like yeah. So what's the size? What's the number of end hosts or some quantification of the size of the data plane?
The measurement study shows that in a small network environment, desktop will ought to be enough. But if the network size larger, for example, larger than 1,000 or some larger, and data plan will experience some delays because its capability will be a bottleneck. But the exact measurement,
I myself have tested it out with 400-ish nodes generating something on the order of a couple hundred flows per, and one controller was enough for that. So we're talking 4,000 flows per second. And so, like, in order to get to the point where you're actually worried about controller resources, you're going to have to build really large networks.
Because in our real-world implementation, they only use two desktop to control about a small switch group, about eight switch groups. They also have some simulations. The simulation,
yeah, you can use Mininet.
The simulation scale is about 2,000 or so.
2,000 flows a second.
Yeah. You mean the forwarding speed?
Yeah, like I'm asking what's the density of flow setup that's going into the control plane, and that warrants needing a scalability concern.
The exact number in the simulation, I forgot the exact number. Later we can show
okay.
the implementation. The scalability problem arises, and the two metrics will be a concern: the response time and the throughput. The response time is the time that a flow that goes through the switch and then will be forwarded to another port. The time difference between the two times points. And the throughput means that how many flow requests will be processed within a given time. So the two metrics will be the scalability concern in the STM control plane. Since it's a challenge to build a scalable controller, but if we use a single controller in the network, the I/O and the computing power will be a bottleneck of the whole network. That's a problem of the single controller design. How to solve the problem? We can first give some design spaces. We can approach this problem from two opposite directions. One direction is a straightforward approach. That is, we solve the problem within the control plane. Since the controller is a bottleneck, then we can improve the performance of the controller from different directions. One possible direction is to improve the executing efficiency of the network operating system. That is, revise the code of the operating system to get a controller with more capabilities. That is, there are some work doing this. And we also can provide some multi-threading techniques to solve the controller problem. This is also use a single controller, but we can revise the code to get a higher performance. Another direction to solve the control problem is to provide a distributed control plane. And there are also some works on it from the Hyperflow and some work from the SDN. That is, since one controller is not enough, we can use multiple controllers. That is, to balance the load among different controllers. It will therefore solve the bottleneck problem. And another direction to solve the problem is to have the problem solved in the data plane. Since in the SDN framework, all the control functionality is implemented in the control plane. But the control plane is now a bottleneck. We can then push some functionalities to data plane. For example, the two work different in the data flow. They all push some functionalities to the data plane from the data flow, and they push the short-lived flows to data plane. That is, the data plane can solve the forwarding decisions and without sending the request to the control plane. So the requests are much smaller than the traditional design. So the two options are, the two design options are all feasible and now is also very popular. In our design, we focus on the single controller design, but the single controller is a cluster design. Because if we use a single controller, the memory and CPU and network bandwidth will be limitations. So how to guarantee the scalability and reliability? We can use a scalable cluster approach. Since we have multiple controllers in the design, but how to balance the load between the multiple controllers and how to implement the intercommunication between the multiple controller will be a problem. So we will explain how to design the approach. In our design, we use multiple controllers. Since single controller is a bottleneck, then we use multiple controller. But the multiple controllers will be organized into a logically centralized one. And the design is also transparent to the northbound and southbound APIs. That is, the southbound API is OpenFlow and northbound API is the APIs between the applications. And the design also considers the scalability and reliability support. The basic idea of our design is that we organize the microcontrollers into a cluster, and then the cluster will be regarded as a single controller. So with this design, the performance of one cluster will be much higher than the previous single design.
Are you slicing out your data plane then, and handing responsibility of a different slice of the data plane to the controller?
No, we don't slice the data plane.
Because then you have a problem with your bottleneck, because all the flow entries have to be triaged into your cluster, and that triage point now becomes the bottleneck.
Actually, you mentioned this is one of the problem, but with load balance design, we can balance the load between different controllers.
Right, but the question is, who handles the prioritization of the incoming flows from the data plane? If they're all going to the same, if you're treating the controller as the same thing, then as all the flows come into the control plane, you still have to distribute those flows amongst the controllers.
Yeah.
And that distribution process now becomes the bottleneck.
Yeah, that's the problem we will solve. That's the problem we will solve.
Maybe the processing power is much shorter.
Yeah, you have to do something smart with the triage, but the question is what?
Right, but that's like a usual problem for multi-processor and then parallel computing, like for many years, right?
Yeah.
Is there anything new?
Actually, there's nothing especially very novel in the design. Just use a simple algorithm to balance the load.
Sure.
Yeah.
Okay.
The key feature of the design is that we use a control cluster. That is, the cluster includes many control units. The units can balance the load from the data plane. It's a centralized design. And the intercommunication is implemented. The state information intercommunication is implemented using a single database for control information. That is, all the control units share the same logical database. That is to keep the consistency. And the node balance between the controllers is implemented by an inner SDN network. That is, in our design, the controller is implemented using an SDN framework. So it's a recursive design. That is, the controller itself is also a SDN network. That's the architecture of our design. This square represents the overall view database. That is, all the control units will share this control information, and all the controller units will balance the load from the SDN data plane. And this load balancer will be responsible for balancing the load. And the load balancer actually itself is a SDN network. That is, it consists of some OpenFlow switches and inner controller. So the logically centralized controller itself is a SDN network. So with this design, the scalability can be achieved with the recursive design. That is, if the load becomes very high, we can recursively design the load balancer. That is, it's a SDN network. If the load on the load balancer is also high, we can use another inner SDN network to achieve this scalability.
I just have a simple question. So I'm trying to understand the hardware architecture here. When you say controller pool, each controller unit is a thread or processor, or it's actually a processor?
Processor or even a laptop desktop.
Oh, it could be a processor in a multi-processor machine, or it could be a machine by itself.
Yeah.
Okay.
It's not a logically one. It's actually a physical one.
Okay.
It is a physical processor or physical machine.
All right. And they're connected with the load balancer, of course, through what kind of connection?
The connection with the load balancer is using a hierarchical design. The hierarchical design is that each machine is connected to several others. Each machine is connected to the load balancer. Actually, the load balancer is a SDN network. And each control unit is connected to multiple switches. And the switch
I see.
are interconnected using a specific architecture topology.
So the cluster controller is actually a data center network.
You can regard it as a data center, or you can regard a small SDN network. Yeah. With this design, the control cluster now is regarded as the automatically centralized one. So it's transparent to the southbound API, that is OpenFlow, and it's also transparent to the applications. So the programming paradigm is remain the same as the previous one. And the load balance control is achieved by the load balancer, which is implemented using SDN network. We can use a software router or program router to implement it. And a load balancing algorithm is used to balance the load. Actually, in our design, we only use a simple load balancer algorithm that is evenly assign the load on different controller unit. It's a very simple algorithm.
Yeah.
Concerning the controller core pool, that is the multiple control unit. Each controller core is I/O and the OpenFlow message processing unit. And the pool are composed of many controller cores. And the size of the pool is scalable. That is, we can if we need a high performance controller, we can simply add more process units in the pool. Every core is independent from the others. That is, each core is not aware of other cores. But in this way, we can achieve some fault tolerance. That if one controller core fails, other cores will balance the load. Will evenly balance the load. And we also mentioned that all the control units share the one overall information on the control message. So to implement the cluster controller, that we need a consistent view of the network. So the consistent view of the network is achieved by a overall database.
Excuse me.
Yeah.
What does that apps means there? I mean, what that app is, it's just collecting data somewhere like from this controller.
Sir?
And the apps?
Apps? Yeah, actually the apps were, you can customize your controller, the routing algorithm or some other load balancing algorithm using the apps. That is, you can program the apps to get your customized objective. Okay. In our implementation of the architecture, we use two machines to form the cluster, because we just tested its preliminary performance. It's ongoing work. So in the implementation, we use two servers to form the cluster, and then use 8 OpenFlow switches to form the load balancer. We just mentioned that the OpenFlow, the load balancer is actually a small SDN network. So we use 8 OpenFlow switches to form the load balancer. And we use the POX as the OpenFlow controller. It's an open source network operating system. And we revise some code of the POX to form a cluster to control the cluster. with the two machine cluster, we can balance the control plane traffic and testify and we can verify its effectiveness. That's the environment. That is the two server from the control cluster, and we have a home used router as the OpenFlow switches. We have revised the code of the home used routers. It forms the inner SDN network. The OpenFlow switch has 16 ports and using the OpenV switch software.
Where's your these 4 switches are your control plane SDN. Where's the actual data plane?
The actual data plane is actually simulated. We use some traffic generation to form to implement the actual request. So it's in the real experiment only implemented the cluster controller, and the traffic is generated using other machines. We have some results in this figure that since we have 2 machines to balance the load, we can see that with the increase time, the traffic load that varies, but clearly the 2 controller, controller 1 and controller 2, can share the load of the total traffic load. So that can be regarded as the effectiveness of the load balance results. So we can see that the red solid line is the total traffic load, and this green dash and the red dash are the load of the controller 1 and the controller 2 respectively. So we can see that in average, the 2 controllers shares about half of the load. So we can conclude that the load balancer is somewhat effective. And in this architecture, because when we make the load balance design of we need balance the load between different clusters. There might introduce some processing delay if we use the load balance design, because in the inner SDN network, if we redirect some traffic to other machines, we have to choose another. We have to choose another routing path. So another routing path may be somewhat will experience longer delays. So the processing delay will be slightly higher than the original shortest path. In summary, that for single controller, I/O will be bottleneck, and the controller may be scale, use a cluster. In the cluster design, 2 important questions is load balance and interconnection. In my slides, I omitted the design detail of the interconnection. Actually, interconnection is using a hierarchy design. That is the inner SDN network switches are interconnected using a hierarchy design. Each switch is connected to multiple other switches using a specific algorithm. So that's my talk, and your comments are very